Okay, bienvenidos a lesson 10. So we're going to look at common continuous random variable distributions. So now that we introduced, hey, what is a continuous random variable? How do we find the expectation, variance, and standard deviation, whatnot? Now we're going to look at special cases. So there are certain random variables that we could say, oh, we know that this is, say, a uniform distribution. It has a certain form for its PDF, and it also has a certain form for its expected value as well as its variance. Makes it much easier to calculate, so that's pretty great. By all means, you can still go ahead and use the definition, the integral definition of expected value as well as for variance, but just know that if you are able to say, hey, I know this is a uniform distribution, there are shortcuts you can use, which is great. So common distributions. So the first one we're going to talk about, at least in this lesson, is going to be the uniform distribution. So it's symmetric. That means if I were to fold it in half in the middle, it matches on the other side. It's perfectly symmetric. In fact, it's specifically shaped like a rectangle. So uniform, it's probably the most straightforward. Pretty much you have a range of values and you have one height. There's no fluctuation. It's just a rectangle. It's constant probability. It is the simplest by far. Absolutely, you can use integration here, but it's one of those, if you're comfortable finding the area of a rectangle, you could also use, just that width times height. Gamma. So gamma has a lot of special cases that we could use. So it is skewed, and so not only that, it is right skewed. At least here it is. Although it depends. This particular example is right skewed. But we'll go into more of that on week 3. When it's skewed, it means that, hey, it's not symmetric. More values are pushed to one side than the other. So this particular example is positive skewed. We have special cases. There's the exponential distribution. There's the Weibull, which you'll see in your data analysis assignment, as well as chi-squared. And that's not all of them, but that's just a few that are commonly used to model things in engineering. And then the normal distribution, which even if you haven't heard of it, chances are you've seen it somewhere. Goodness knows I've seen this normal curve, this bell-shaped curve, in so many commercials, and I kind of laugh. It is the most commonly used distribution in statistics. It is perfectly symmetric, so if I fold it in half, it matches exactly on both sides. Definitely very, very frequently used. So, the uniform distribution. It's the one we're going to go into first. It's what this lesson's about. So we are looking at a continuous random variable from some value A to B. So it's going to go from A to B. It is going to be a rectangle. So all of the values here have an equal likelihood of occurring. It's shaped like a box or a rectangle. A lot of times people use this for random number generators, saying, hey, I want you to pick a number between A and B, and randomly pick a number from there. So a lot of those times when we generate random numbers, this is one of the ways we do it. Things to note, which I believe we will mention anyway, the total area under any of these PDFs has to total to 1. So if this distance here is B minus A, this means that this height of the rectangle is 1 over B minus A. So the idea is my area is, I'm going to say height times width. So it's going to be 1 over B minus A times B minus A. These will cancel and you'll get 1. So things to note, a lot of times we'll give you this information and we'll expect you to find the height. So the example we're going to be using throughout this lesson, we have a large conference room at some university. People can go ahead and reserve the conference room for anywhere between 0 and 4 hours. Although, admittedly, I probably would not bother reserving a room for 0 hours. Just a note. So the meetings occur often and are varying lengths. And for this example, we are going to assume that the length of a meeting is our random variable x here, and it has a uniform distribution from 0 to 4 hours. So here's an example here. We have that rectangle drawn around, so from 0 to 4 hours, which means the height here, it's going to be 1/4 or 0.25 because we have a width here of 4 hours. So here we are getting into that height here. So a variable that has a uniform distribution from A to B. So A is the lower value, B is the upper value. It has that width B minus A, and that means our height has to be 1 over B minus A because the probability has to be equal to 1. This is true no matter what random variable we're looking at. If I have a discrete case and I add up all the probabilities, those have to add to 1. Same with a continuous distribution. If I go ahead and I sum up or integrate all the probabilities into the curve, that total area has to be equal to 1. So I do have to ensure that this is my height here. So my PDF here is just going to be 1 over B minus A. And B and A are numbers. And this is true when x is between A and B. And then note that, so this right here, this is me defining my sample space. So this is the PDF, and specifically for when x is between A and B. Then my PDF is going to be 0 everywhere else. So that means if you're higher than B, it's 0. If you're lower than A, it's 0. It's just, there's no area there. So the expected value and variance, they can be calculated the same way, where you say, oh, my expected value of x. It's still going to be, so from A to B times x times 1 over B minus A dx. It does have a nice general form though. Oops. And that's A plus B over 2. It's quite literally the average of your endpoints. It's pretty handy there. Your variance is a tiny bit trickier, so you want to take that difference, B minus A, square it, and then divide by 12. There are some theoretical reasons why the number is 12. We're not going to go into that in this class. Just know there is a reason. So here specifically, we're using A as the lower bound, B as the upper bound. And just note that the area of the rectangle is, I'm going to do height times width. I probably used other letters back in the day. It's just that 1 minus B over A times B minus A equal 1. And this is going to be true for any continuous random variable we have. The area under the entire thing should be 1. The area under the entire thing where x is in the sample space. So now we're going to go on to our conference room example. So this is that scenario where people can go ahead and reserve the conference room for anywhere between 0 and 4 hours. And we're going to assume that x, which is the meeting length for reservations, is uniform from 0 to 4 hours. So drawing the distribution here, absolutely you can draw it up against the axis. I have a tendency to just draw a rectangle first. If you know it's uniform, you immediately know what shape it has. And from 0 to 4 hours, so I'm going to have hours here. So from 0 to 4 hours. Things to note, the length here, 4 minus 0 is 4, which means the height here for my probability, it needs to be 1/4. It's okay if you write 0.25, that doesn't really make a difference. But the idea is the height needs to be 1/4 for the area in the entire rectangle to be 1. So then what is my probability distribution function? So f of x, it's going to be, so 1 over b minus a, that's just going to be 1 over 4 minus 0, which is 1/4. So it's going to be 1/4 for any x value between 0 and 4. So for x between 0 and 4. And then I'm going to have no probability anywhere else. To be fair, you can't actually reserve any conference room for negative amounts of time, right? Short of having an actual time machine. But this also indicates that it's strictly not allowed to have conference reservations for longer than 4 hours. So 0 else. So then what is the average length of a meeting in the conference room? So it's asking for my expected value. Definitely, this is a great place to pause and try it first yourself. But if not, it's going to be what? Just b plus a over 2. So 4 plus 0 over 2 is going to be 2. And remember, x is reservation time in hours. So I'm going to put hours. So on average, out of all of these reservations being made, the average reservation is being made for 2 hours, given that it has this distribution. Then how much does meeting time vary on average? It's specifically asking us for the standard deviation of x. So as any time when we're calculating the standard deviation, we're going to find the variance first. And once we find the variance, then we're going to square root. So once again, this is a really good time to pause and attempt this yourself. But I'm going to go ahead and I'm going to have it set up here. So b minus a squared over 12. So this is just going to be 4 minus 0 squared over 12. So 4 squared is 16. 16 over 12. You could reduce it 4/3. So this is my variance. Remember that I want the standard deviation. So, I'm going to now square root. So my standard deviation is just the square root of that. So the square root of 4 over 3. And it's going to be, I round it a little bit. It's going to be about 1.155 hours. So it seems that the meeting times or reservation times vary on average about 1.55 hours from that average of 2 hours. So things to note is expected value as well as standard deviation will have the same units as whatever that random variable x has. One of the reasons we tend to talk to clients less often about variance specifically is because the units are squared. So the units for variance in our example would be in hours squared, and conceptually that does not make sense to a lot of people. So we have a tendency to often specifically talk about standard deviation to clients. Although we have a tendency, we really love the variance. It has some really nice calc properties. And since it's a really straightforward transition from variance to standard deviation, we often do variance first. So we're going to continue this example here, still focused on our conference room reservations here. So I'm going to just write hours here. If you want to label the y axis, probability would probably be it. So I want to know how likely is it that a meeting will be less than 1 hour. So probability that x is less than 1 hour. So I'm just going to rewrite this for a second. So it's the same as x being between 0 and 1, right? Because anything under 0 has 0 probability. So if I have 1 hour here, and I'm looking here, you can absolutely integrate. You are welcome to. But know that we know the height of this rectangle, which is definitely not drawn to scale. And we know the width here. 1 minus 0 is just 1. So I can tell you right off the bat the area of the shaded part is going to be 1/4. But you can absolutely use integration here. I would say uniform is probably the friendliest, where you really don't have to necessarily do it to get accurate results. But so from 1/4 dx, so I'm going to get x over 4 evaluated from 0 to 1. So I'm going to get 1/4 minus 0. That's just going to be 1/4. So the probability of me randomly selecting a meeting time made for this conference room and it being less than an hour long, it's going to happen about 1/4 of the time. So then we have a follow-up question. It looks like it's more of a percentile question. So 20% of meetings will be less than how long? So if I were to go ahead and I'm going to go ahead and use this. Obviously not to scale, but if I have this area, I want to know what this value is if the shaded part is 20%. So if 20% are lower than it, I'm looking for the 20th percentile, or the 20th quantile technically. So I'm looking for x 0.20 or x 20 over 100. Either one is totally fine. I'll admit though, if you're typing, it's a lot easier to type out x subscript 0.20 than it is to have that fraction in there. It doesn't type as nicely most of the time. But absolutely, it's your prerogative. So I want to know the value of x here. So I will have the CDF of this x value is equal to percentile. So from 0 is the lowest value to x 0.20, 1 over 4 dx. I'm going to end up getting x 0.20 over 4. And we're going to set it equal to that 20%. This is going to be very, very easy as far as math goes. I'm going to end up getting x 0.20 is equal to, multiply 4 by both sides, 0.80. So what this is saying is if that only 20% of all the conference room reservations are being made for less than 0.8 hours. If you want a translation, you can. I switched to minutes just to understand. It's implying that, hey, only 20% of all the reservation times being made are for 48 minutes or less. Absolutely, you're welcome to transition there. I would keep, up until this point, everything in hours since it's in hours. But just know that if we give you one in hours and we give you another in minutes, you should switch everything to one or the other. And it's totally fine, whichever you choose to do. Just keep in mind, you don't want to mix and match units. You want to have the same units everywhere. This was just me kind of translating at the end. So this was an hour, so I kept everything else in hours. But if they ask me, hey, what's the probability there's a meeting that's less than 90 minutes? I would either need to switch that to 1.5 hours, or I would need to go ahead and just switch my distribution to be in minutes, so they're all in the same units. So just to note, And that should be our bit on uniform distributions. So coming up next is going to be gamma and exponential. We're also going to mention the chi-square distribution. And yeah, we'll see you there.